At what moment in the cosmos did the first light appear? How did it come to bathe a universe that, in its earliest moments, was pure darkness and chaotic energy? The story of light is, in many ways, the very story of the universe. From the very instant everything began, light has been both witness and protagonist of the most transcendent events in the cosmos. Every photon traveling through space is an ancient messenger carrying information about stars, galaxies, and phenomena that occurred billions of years ago. Without light, it would be impossible to discover what lies beyond our atmosphere, understand what we are made of, or how the elements that form our planet and our bodies evolved. But light is not just a tool for observation, it is also a transformative force. It has shaped matter, defined the limits of our knowledge, and, in its journey, has been captured, bent, and transformed by black holes, gas clouds, and magnetic fields. It is the key to revealing the secrets of dark matter, deciphering the distant past, and anticipating the future of the universe. Why is the speed of light the cosmic limit? What does the color of a star tell us about its age or composition? How can light, invisible to our eyes, reveal cataclysms as violent as supernova explosions or galaxy mergers? Throughout time, light has guided the evolution of life on Earth and inspired humanity to look up, to explore, and to question. It has been an ally to scientists, philosophers, and dreamers alike. In every corner of the universe, in every moment of cosmic history, light has left its mark, from the first flashes after the Big Bang to the artificial light we use today to communicate and explore the boundaries of knowledge. Understanding the history of light is, ultimately, understanding how the universe has transitioned from absolute darkness to the astonishing diversity of phenomena we are now capable of observing. How far can light take us in our quest to understand the cosmos? What happened in the first moments of the universe for light, that familiar and mysterious phenomenon, to exist? Let's go back to the very beginning of everything, the Big Bang. Approximately 13,800 million years ago, the universe was born in an explosion of unimaginable energy and matter. But did light exist from the very first second? The answer is more fascinating than it seems. During the first fractions of a second, the universe was an ocean of pure energy, incredibly hot and dense. In this primordial soup, temperatures exceeded billions of degrees, and fundamental particles, like quarks and electrons, danced without forming atoms. Light, in the form of photons, was already present, but it was not the light we know and see today. In that extreme chaos, photons constantly collided with other particles, unable to travel freely. It was like trying to see through a fog so thick that light couldn't move an inch without being absorbed or deflected. Why couldn't light escape? Imagine a room full of people where every step you take, you bump into someone else. That's how photons lived, trapped in the cosmic soup. However, as the universe expanded, that energy began to cool down little by little. With the expansion, conditions changed, and although light remained imprisoned, the stage was being set for a crucial transformation in cosmic history. A surprising fact is that in those early moments, light was so powerful that it dominated over matter itself. All the energy of the universe was in the form of radiation and elementary particles. This stage, where matter and light were so intertwined, laid the groundwork for everything that would happen afterward. Thus, the birth of light was not a single moment, but a process linked to the evolution of the universe itself. How did light finally manage to free itself and travel through the cosmos? That mystery would mark a turning point in universal history. Did you know that there was a time in the universe when light existed, but could not travel freely? That mysterious period is known as the era of radiation, a fascinating stage in which the energy of the cosmos was almost entirely dominated by light and other forms of radiation. But why, if light was already present, could it not escape? To understand this, imagine the universe as an incredibly dense and hot soup, where particles collided with each other at every moment. Light, in the form of photons, tried to advance, but it was as if it were trying to cross a room filled with thick smoke. Every small advance was interrupted by a collision with free electrons, which constantly deflected and absorbed it. During the first hundreds of thousands of years, the temperature was so high that atoms could not form. Protons and electrons were separated, creating an opaque plasma. In this environment, light could not travel large distances without being absorbed or scattered. Can you imagine a flashlight trying to shine through a solid wall? That's how difficult it was for photons to traverse the universe at that time. Radiation, although abundant, was trapped, bouncing back and forth, unable to carry information or illuminate space. Why was this stage so crucial? Because the enormous amount of energy in the form of radiation shaped the development of the cosmos. The pressure of that radiation influenced how matter clumped together, preventing gravity from forming structures too quickly. In other words, light played the role of a cosmic regulator, balancing the expansion of the universe and the formation of the first seeds of galaxies and stars. Without this delicate balance, the universe we know today would be radically different. As the universe expanded, the temperature gradually decreased, and radiation began to lose its dominance. However, during the era of radiation, light and matter were so intertwined that their fates seemed inseparable. This period reminds us that light, long before shining freely across the cosmos, was the great invisible protagonist of a young and turbulent universe. What caused the change that finally allowed light to escape from its prison? That is the next big question in the history of light. What happened when the universe was just a few 100,000 years old? At that moment, one of the most significant events in all of cosmic history occurred: recombination and the decoupling of light. Until then, the universe was like a dense hot soup of charged particles, protons, electrons, and photons, all constantly interacting. Photons, or light particles, collided repeatedly with free electrons, unable to travel great distances. It was like trying to move through a thick fog where light cannot advance without being scattered. But what changed for light to finally escape? As the universe expanded and cooled, the temperature dropped to a critical point, about 3,000 degrees Kelvin. This is where the magic of recombination happens. Protons and electrons, previously separated by intense energy, could finally come together to form neutral hydrogen atoms. Why is this process so important? Because as neutral atoms formed, photons stopped encountering free electrons to constantly collide with. It was as if the fog suddenly dissipated and light could travel unobstructed. This moment, known as the decoupling of light, marked the instant when photons began to move freely through the universe. Can you imagine the first time light could traverse the cosmos without being stopped? Those same photons, released nearly 14 billion years ago, still travel through space and can actually be detected today as the famous cosmic microwave background radiation. Isn't it incredible to think that every time scientists study that radiation, they are observing a direct echo of that primordial moment? Recombination and the decoupling of light not only allowed the universe to become transparent, but also laid the groundwork for the formation of the first cosmic structures. Without the constant scattering of photons, slightly denser regions of matter could begin to collapse under gravity, giving rise to the first stars and galaxies. Thus, the universe ceased to be an opaque, chaotic mass and transformed into the luminous stage that now allows us to explore its secrets with the help of light. What if we could observe a photograph of the universe when it was just an infant? There is a silent imprint that runs throughout the cosmos, cosmic microwave background radiation. This light, which fills space in all directions, is the oldest relic we can detect, a direct testimony of the universe's early times. But why is it so special? Imagine the echo of a gigantic explosion. This is what this radiation is like, the luminous echo of the universe when it was only a few 100,000 years old. The cosmic microwave background is like a frozen snapshot of that distant time, when the universe had just become transparent and light could finally travel freely. This light, which was originally as hot as the surface of a star, has been cooling and stretching for billions of years until it reaches us as a gentle breeze of microwaves. In fact, if we had an ultra-sensitive radio, we could pick up some of this ancient glow. Did you know that a small fraction of the static noise you see on analog televisions without a signal comes from this ancestral radiation? Why are scientists so fascinated by this faint microwave background? Because in its tiny temperature, variations lie clues about the composition, age, and geometry of the universe. By analyzing these subtle patterns, astronomers have been able to calculate the age of the cosmos, estimate how much matter and energy it contains, and even deduce how the seeds of the galaxies we see today were distributed. One could say that the cosmic microwave background is like the DNA of the universe. It contains the essential information about its origin and evolution. But how do we manage to observe something so ancient and faint? Thanks to satellites like COBE, WMAP, and Planck, which have scanned the sky in search of these microwaves with astonishing precision. What they discovered is surprising. Although the universe appears uniform in all directions, there are tiny temperature differences on the order of 100,000th of a degree. Those small fluctuations were the seeds of all cosmic structure. Without them, galaxies, stars, and planets would not exist. Thus, the cosmic microwave background is not only a window into the past, but also the key to understanding how complexity emerged from darkness into what we contemplate today. The dark age of the universe is one of the most mysterious and fascinating periods in all of cosmic history. What happened after light managed to break free and travel through space, but before the first stars began to shine? For hundreds of millions of years, the universe was shrouded in absolute darkness, as if it were a vast room without windows where no lamp had ever been lit. But why did this cosmic blackout occur? During this time, the universe was an ocean of neutral hydrogen and helium, newly formed atoms that absorbed and scattered light, preventing any glimmer from traveling great distances. Without luminous sources, there were no stars or galaxies, only a cold and uniform fog that filled everything. It was a total visual silence, in which matter slowly accumulated under the influence of gravity, as if the universe were reserving energy for the grand spectacle that would come later. How do we know this era existed if, in theory, there is no light to reveal it? Although no telescope can directly observe the dark age, astrophysicists have found crucial clues in the cosmic microwave background radiation and in the distribution of the oldest galaxies. It's like trying to reconstruct the plot of a novel by only reading the pages before and after a lost chapter. Mathematical models and computer simulations show us that, during this period, small density fluctuations began to grow under gravity, forming the seeds of future stars and galaxies. The Dark Age ended when the first stars ignited their light, ushering in a new era in cosmic evolution. But until that moment, the universe was a stage of shadows and silence, where matter was secretly preparing for the birth of the first celestial bodies. What would have become of us if the universe had never emerged from that darkness? The answer underscores the fundamental importance of light in the history of everything we know, reminding us that even the quietest periods hold the promise of a bright future. Have you ever wondered how the first stars emerged in the vast dark ocean of the early universe? For hundreds of millions of years, after the birth of the cosmos, there wasn't a single star. The universe was a cold and dark place, populated only by clouds of hydrogen and helium. But what triggered the birth of the first cosmic beacons? The answer lies in gravity and the patience of time. As the universe expanded, small fluctuations in the density of matter caused some regions to be slightly denser than others. Over millions of years, gravity began to compress these gas clumps, making them increasingly compact. It's as if gravity were kneading a ball of cosmic dough, squeezing and squeezing until, finally, the pressure and temperature in the centers of these clouds became high enough to ignite the engine of stars, nuclear fusion. How can a simple cloud of hydrogen transform into a bright star? It all happens when hydrogen atoms, being compressed under colossal pressure, start to fuse and release enormous amounts of energy in the form of light and heat. Thus, the first stars were born, illuminating the darkness and radically transforming the universe. These stars, known as population 3 stars, were gigantic compared to the current sun and composed almost exclusively of hydrogen and helium, as heavier elements did not yet exist. But why were these first stars so important? They not only broke the cosmic night, but also initiated a chemical revolution. In their cores, they manufactured the first heavy elements, such as carbon, oxygen, and iron, which would be expelled into space when these stars died in titanic explosions. Thus, the first stars not only brought light to the universe, but also sowed the necessary ingredients for the formation of planets, galaxies, and eventually, life. The birth of stars marked the beginning of a new era in which matter and light began to write the history of the cosmos together. What happened when the universe stopped being a dark and silent place to transform into a stage filled with light? This fascinating moment is called rionization, a key process that marked the cosmic awakening. But why is rionization so important and what triggered it? To understand, we must imagine the universe as a vast fog of neutral hydrogen. For hundreds of millions of years, that fog absorbed light, preventing it from traveling great distances. Everything changed when the first stars and galaxies were born. Their radiation was so intense that it began to break apart hydrogen atoms, ionizing them and dispersing the cosmic fog. What exactly does rionization consist of? It is the process by which ultraviolet radiation from the first luminous sources strips hydrogen atoms of their electrons. In other words, neutral hydrogen transforms into ionized hydrogen, allowing light to travel freely through space. This phenomenon did not happen overnight. It was gradual and occurred between the first hundreds of millions and 1 billion years after the origin of the universe. Imagine it as a cosmic dawn, where light gradually conquers darkness, creating bubbles of transparent space around each newborn galaxy. Is it possible to know what this process was like? Astronomers have found clues by observing distant galaxies and quasars, which act as flashlights in the background of the universe. By analyzing the light that reaches us from these objects, they can detect the presence of neutral hydrogen along the way. If the light is absorbed at certain wavelengths, it means there are still regions that are not rionized. But if the light travels unobstructed, we know that area is primarily composed of ionized hydrogen. In this way, scientists reconstruct a map of the primitive universe, discovering how and when rionization progressed. Why is rionization fundamental to cosmic history? Without it, the universe would remain opaque, and the light from stars would never have reached us. This process allowed information to travel through space, revealing the structure of galaxies and paving the way for the formation of new elements and planetary systems. In a sense, rionization is the moment when the universe becomes visible, allowing humans, billions of years later, to contemplate its history through light. How is it possible that from an initially homogeneous universe, the majestic galaxies that now populate the cosmos have emerged? The key lies in the interaction between light and matter, a play of forces that shaped the first cosmic structures. After the initial cooling of the universe, small fluctuations in the density of matter marked the fate of entire regions. Where there was a little more matter, gravity began to concentrate it, forming the first outlines of galaxies. But what role did light play in this process, seemingly dominated by gravity? Far from being just a spectator, light was a fundamental actor. The first stars illuminated their surroundings and, in doing so, emitted ultraviolet radiation capable of heating and pushing the surrounding gas. This radiation could halt gravitational collapse in some regions, while in others, by ionizing hydrogen, it allowed the gas to cool faster and collapse even more efficiently. It's as if light sometimes acted as a barrier and other times as a catalyst, deciding where and when new stars would be born and consequently galaxies. The formation of a galaxy is comparable to the organization of a large city. Dark matter provides the invisible infrastructure, but light, released by stars and explosions, regulates the pace of construction and expansion. Through radiation, the first stars and black holes exerted a far-reaching influence, affecting the birth of other stars even hundreds of thousands of light years away. This interaction not only determined the shape and size of galaxies, but also their ability to create new stellar systems. Did you know that astronomers can reconstruct the history of galactic formation by observing the light that reaches us from deep in the past? Each galaxy is like a luminous archive. Its color, brightness, and chemical composition reveal episodes of star formation, mergers, and explosions. Even today, light remains the primary messenger that allows us to understand how galaxies are born, grow, and evolve, reminding us that the history of light and that of galaxies are inextricably intertwined. What happens when a star, much more massive than our Sun, reaches the end of its life? The answer is one of the most spectacular and violent events in the cosmos, the supernova. For millions of years, these stars fuse light elements in their cores, transforming hydrogen into helium, then into carbon, oxygen, and so on until they reach iron. However, iron marks a limit. Fusing it does not release energy, and the stellar machinery comes to a halt. So what happens then? The star collapses on itself in a matter of seconds, releasing an unimaginable amount of energy and causing an explosion that can shine as brightly as an entire galaxy. But why are supernovas so important? Beyond their dazzling flash, they are true factories of heavy elements. At the moment of the explosion, temperatures and pressures reach extreme values, allowing the formation of elements like gold, silver, uranium, and many others that cannot be created within stars in normal states. Have you ever wondered where the calcium in your bones or the iron in your blood comes from? The answer is, quite literally, in the ashes of ancient supernovas. Without these cosmic cataclysms, the universe would be much poorer in chemical diversity. The light emitted by supernovas is so intense that, for brief periods, they can outshine all the stars in their host galaxy. Some of them, called Type Ia supernovas, have served as cosmic beacons to measure distances in the universe and reveal the mysterious acceleration of cosmic expansion. How is it possible that such a fleeting explosion has such lasting consequences? The echo of the light and the elements ejected by a supernova travels for millions of years, seeding entire regions of space with the material necessary for the formation of new stars, planets, and eventually, life. Supernovas also leave behind fascinating remnants, bright nebulae, incredibly dense neutron stars, or even black holes. These remnants continue to influence their surroundings long after the explosion has ended. Thus, each supernova is both an end and a beginning. It represents the death of a star, but also the birth of new worlds and possibilities. Ultimately, each of us carries within us atoms forged in the heart of a supernova. We are, in a sense, children of light and stellar fire. What happens when light encounters one of the most mysterious objects in the universe, a black hole? At first glance, we might think that light simply disappears, but the reality is much more fascinating. Black holes, with their intense gravity, distort the space-time around them in such a way that not even light can escape from within. The boundary beyond which nothing can escape, not even a ray of light, is called the event horizon. This boundary is like an invisible frontier. Once light crosses it, it is trapped forever. But does this mean that black holes are completely invisible? Interestingly, no. Although we cannot see the inside of a black hole, we can observe the effects they produce on the light and matter around them. When a star or a cloud of gas approaches a black hole, the matter is drawn in and forms an accretion disk. In this disk, particles move at extreme speeds, generating such intense friction that the matter reaches temperatures of millions of degrees. As a result, large amounts of light are emitted, especially in the form of X-rays, which we can detect with special telescopes. Thus, black holes, although they are light devourers, can shine brightly thanks to this accretion radiation. Another intriguing question: can the gravity of a black hole alter the path of light passing nearby without being swallowed? The answer is yes, and this phenomenon is known as gravitational lensing. When the light from a distant star passes near a black hole, gravity curves its path, just as a lens bends light in a pair of glasses. This can cause us to see distorted, duplicated images, or even rings of light called Einstein rings. These effects not only confirm the predictions of Einstein's general relativity, but also allow us to detect the presence of black holes, even if they do not emit their own light. Finally, an even stranger question arises. Can a black hole emit any kind of light? In 1974, Stephen Hawking proposed that, due to quantum effects, black holes could emit an extremely faint radiation, now known as Hawking radiation. Although it has never been directly detected, this theory suggests that even the darkest objects in the cosmos are not completely silent. Thus, the relationship between light and black holes is a complex dance, where absolute darkness and the most extreme energy intertwine to reveal the deepest secrets of the universe. Can light be bent? Although it may seem incredible, the answer is yes. Gravity, that force that makes everything fall to the ground, can also curve the path of light. This revolutionary idea was proposed by Albert Einstein in his theory of general relativity. According to him, massive objects, like galaxies or galaxy clusters, deform the space-time around them, and light, when traveling through that curved space, follows paths that appear to bend. This is how the concept of gravitational lensing was born, one of the most astonishing and useful phenomena in modern astronomy. But how does a gravitational lens work exactly? Imagine the universe as a stretchy sheet and you place a heavy ball in the center. If you try to roll a marble nearby, its path will curve around the ball. The same happens with light. When it passes close to an extremely massive object, its path curves, as if it encounters an invisible detour. This deviation can be so intense that the light from a distant galaxy, when passing near another massive galaxy, gets multiplied, stretched, and can even form arcs or rings of light in the sky, known as Einstein rings. Why is this phenomenon so important for science? Gravitational lenses not only confirm Einstein's prediction, but they have also become powerful tools for astronomers. They allow us to observe very distant and faint objects that would otherwise be invisible. It's as if nature lends us a giant telescope, amplifying the light from distant galaxies and quasars. Furthermore, by analyzing how light curves, scientists can weigh invisible objects, such as dark matter, since it also influences the path of light, even though it emits no radiation. Did you know that thanks to gravitational lenses, we have discovered galaxies formed shortly after the Big Bang and have been able to study planets outside our solar system? They have even helped detect the presence of dark matter clusters that would otherwise be completely undetectable. Thus, light, under the dominion of gravity, becomes a messenger that reveals hidden secrets in the deep universe, showing us that reality is much more surprising than our senses can perceive. Have you ever wondered if all the light that exists is visible to our eyes? The answer is surprising. Only a tiny fraction of the light in the universe is perceptible to us. What we call light is merely a thin band within the electromagnetic spectrum, a vast family of waves that includes diverse phenomena such as radio, microwaves, and gamma rays. The electromagnetic spectrum is, in essence, the complete catalogue of all the ways energy can propagate through space in the form of waves. Each type of wave differs by its wavelength and frequency, which we could imagine as the height and width of a wave in the sea. From radio waves, which can measure several kilometers in length, to gamma rays, with wavelengths smaller than the nucleus of an atom, the spectrum encompasses an impressive variety. Long radio waves are responsible for transmitting music and news to our devices, while microwaves heat food in seconds. Beyond that are the infrared waves, invisible but essential. They allow us to detect heat and explore regions of space hidden behind interstellar dust. Next comes visible light, the rainbow that our eyes can capture, with all its colors from red to violet. However, the journey doesn't end there. Ultraviolet rays, although invisible, can cause skin burns and are used by certain animals for navigation. Higher in energy are X-rays, capable of penetrating our bodies and revealing bones in an X-ray image. And at the most energetic end, we find gamma rays, messengers of the most violent events in the cosmos, such as the explosion of a supernova or the collision of neutron stars. Each of these forms of light carries unique information about the universe, functioning like different languages that scientists have learned to decipher. The electromagnetic spectrum is, in fact, a key tool for unraveling the secrets of the universe. How do we know what stars are made of? How do we identify distant planets or discover black holes? The answer lies in analyzing the light they emit or absorb in different regions of the spectrum. It's as if each type of electromagnetic wave offers us a different window to observe reality, revealing everything from the most everyday processes to the deepest mysteries of the cosmos. Understanding the electromagnetic spectrum is understanding that the universe speaks to us in many languages. We just need to know how to listen. How do we know that there is something we cannot see, touch, or directly detect? This is the paradox of dark matter. Although light is our cosmic messenger, dark matter is, by definition, invisible to any type of light, from radio waves to gamma rays. However, light provides us with the necessary clues to uncover its presence. When astronomers observe galaxies, they notice that stars rotate at such high speeds that, if only visible matter existed, they should be flung out into space. What keeps them together? The only explanation is a vast amount of invisible matter, known as dark matter. Light also helps us map the distribution of this mysterious substance. For example, the phenomenon known as gravitational lensing occurs when the gravity of large concentrations of matter, such as galaxy clusters, bends the path of light coming from objects situated behind them. By analyzing how the image of distant galaxies is distorted, scientists can deduce where dark matter is, even though they never see it directly. It's as if dark matter were an invisible sculptor that deforms the path of light at will, revealing its shape through the traces it leaves behind. Moreover, dark matter influences the formation of galaxies and the grand cosmic web. Without it, galaxies would not have been able to cluster or remain cohesive in the early universe. But how do we know this if we cannot see it? The answer lies in the study of the background light from distant galaxies and in computer simulations. Only by including large amounts of dark matter can models reproduce the structures we observe today. Thus, light acts as a detective and witness, allowing us to reconstruct the history and evolution of the cosmos, despite the presence of this enigmatic component. Will we ever be able to directly detect dark matter? So far, all experiments have been unsuccessful. However, the search continues, and light remains our primary tool. Every time a galaxy spins too fast, every time the image of a star bends unexpectedly, light whispers to us that there is something beyond the visible. The relationship between light and dark matter is a reminder that, although darkness may seem to dominate, we can always find ways to unveil its secrets. What connection can light have with one of the greatest mysteries of the cosmos, dark energy? To understand this, we must first ask ourselves, how do we know that the universe is expanding faster and faster? The answer lies, surprisingly, in the very light that reaches us from the farthest corners of the cosmos. Astronomers have used the light from very distant supernovae, known as Type Ia supernovae, as if they were cosmic beacons. These stellar explosions have such predictable brightness that they serve as rulers to measure distances on unimaginable scales. By observing them, scientists notice that the light we receive from them is not only dimmer than expected, but also shows a greater redshift. This means that galaxies are moving away faster than what a constant expansion would dictate. But what drives this acceleration? Here is where dark energy comes into play, a mysterious form of energy that, according to observations, makes up about 3/4 of all the energy content of the universe. Although it cannot be observed directly, dark energy leaves its mark on the way light travels through the cosmos. If we imagine light as a messenger traversing a constantly changing landscape, dark energy is like an invisible force stretching that landscape, making the messenger's journey longer and faster. Thus, the light from very distant objects allows us to reconstruct the history of universal expansion and, with it, infer the existence of this enigmatic energy. One of the most powerful analogies is to think of light as the echo of a shout in a gigantic cavern. If the cavern were to expand while the echo travels, the sound would weaken and distort. Similarly, the light from distant galaxies reaches us weaker and stretched, revealing not only the distance, but also the conditions of the universe during its journey. Thanks to this phenomenon, scientists have been able to detect that the expansion of the universe not only continues, but is accelerating more and more. Light is, ultimately, the fundamental tool that has allowed us to discover dark energy, one of the greatest enigmas of current physics. Without the information provided by light, the acceleration of the universe and the existence of this strange form of energy would remain hidden in darkness. Every photon that arrives from the far reaches of space is a crucial clue to understanding why the cosmos behaves so unexpectedly. And it reminds us that, although dark energy is invisible, its influence is revealed in the journey of light through time and space. Why is there a maximum speed in the universe? This question has intrigued scientists for centuries. The answer lies in the nature of light. Nothing travels faster than it. The speed of light in a vacuum, approximately 300,000 kilometers per second, is not just an impressive number, it is a fundamental limit of physics. But why does that limit exist? Einstein's special relativity gives us the key. If something attempted to exceed that speed, it would require an infinite amount of energy. That's why light sets the cap, the maximum allowed by the laws of the cosmos. Can you imagine sending a message to another galaxy and receiving the reply after millions of years? Such is the vastness of the universe. The speed of light determines how long it takes for information to travel from one point to another. This means that when we look at the stars, we are actually seeing the past. The light that reaches our eyes today may have left its source long before humanity existed. For this reason, in a sense, telescopes are true time machines, allowing us to peek into distant epochs thanks to this universal limit. The speed of light also imposes surprising restrictions on our daily lives and technology. For example, although radio signals and fiber optic communications travel at speeds close to that of light, there is always a slight delay. When you talk to someone on the other side of the planet or control a robot on Mars, that limit becomes evident in the wait, even if it's just fractions of a second or several minutes. No engineer or technological advancement can bypass this rule. The speed of light is an insurmountable wall. This limit has even deeper consequences for the structure of the universe. According to modern physics, no information or material can propagate faster than light. Thus, the concept of simultaneity becomes relative. Two events that seem to occur at the same time from one viewpoint may not be so from another moving at high speed. The speed of light connects space and time into a single entity, space-time. In this way, light not only illuminates the universe, but also defines its own rules and boundaries. Can there be anything more fascinating than a universal constant that, at the same time, reveals the past and delineates the future? What if the light we see from the farthest stars is not exactly the same as the light they emitted when they were born? This question leads us to one of the most fascinating phenomena in astronomy, Redshift. When we observe distant galaxies, we notice that the light reaching us is shifted toward the red end of the spectrum. But what does this mean, and why does it happen? Redshift is, in essence, a cosmic clue about the expansion of the universe. Imagine an ambulance approaching with its siren on. The sound seems higher pitched as it comes closer and lower pitched as it moves away. This is the Doppler effect, and something similar happens with light. If a galaxy is moving away from us, the light waves it emits stretch, causing the light to become redder. The faster the speed of recession, the greater the redshift. But here, something even more surprising happens. On cosmic scales, it's not just that galaxies are moving, but that the very space between them is expanding, stretching the light on its journey through the universe. Now, why is this phenomenon so important? Redshift allows us to measure unimaginable astronomical distances and, above all, to reconstruct the history of the universe. Edwin Hubble, by analyzing the light from numerous galaxies, discovered that almost all are moving away from us, and that the farther they are, the faster they move. This relationship is known as Hubble's law and is the most compelling evidence that the universe is expanding from a common origin. Furthermore, by studying the redshift in the light from extremely distant objects, astronomers can peek into times in cosmic history when Earth, the Sun, and our galaxy did not yet exist. Can redshift tell us anything more? Of course. It helps us identify extreme phenomena, such as the presence of supermassive black holes that consume matter and emit jets of radiation, or the explosion of massive stars in supernova. It even allows us to trace the mysterious dark energy responsible for the acceleration of the universe's expansion. Every time we measure the redshift of a galaxy, we are, in fact, reading an ancient message, a remnant of the past that traveled billions of years to reach us. In short, redshift is much more than a simple change in color in light. It is a fundamental tool for understanding the size, age, and fate of the universe. Thanks to it, astronomers can reconstruct cosmic evolution, uncover mysteries yet to be solved, and above all, remember that when we look at the sky, we are actually seeing the past written in light. What really happens when light travels through the universe? Although it may seem that light simply moves unobstructed, the reality is much more complex and fascinating. Light can be absorbed and emitted by matter in ways that completely transform what we perceive of the cosmos. But how does this process happen? Every atom and molecule in space acts like a kind of special gate, capable of interacting with light only under certain circumstances. It's as if matter has very selective preferences. It absorbs some frequencies of light and lets others pass through, thus determining the image we receive of the universe. Light absorption occurs when atoms, upon encountering a photon, the elementary particle of light, with the right energy, trap it. At that moment, the photon disappears, and the energy it carried is used to excite the atom, causing one of its electrons to jump to a higher energy level. This phenomenon is fundamental both in interstellar space and in our daily lives. In fact, it is the same principle that allows plant leaves to capture sunlight for photosynthesis. But in the universe, these captures of light leave unmistakable traces. Dark lines in the spectra of stars, known as absorption lines, which reveal the chemical composition of objects located billions of light years away. Now, what happens with light emission? After absorbing energy, atoms cannot remain excited forever. Sooner or later, the electron returns to its original state, releasing the extra energy in the form of a new photon. This photon has a specific wavelength, which means that each chemical element emits light with a very particular color. If you have ever seen fireworks and marveled at their intense colors, it's the same principle in action. Each chemical compound emits different light when energized. In space, nebulae shine due to the emission of light by excited atoms, creating cosmic landscapes of stunning beauty. These processes of absorption and emission are key to understanding the history and evolution of the universe. Thanks to them, astronomers can decipher the fingerprints of light that reach Earth and reconstruct what elements are present in distant stars, galaxies, and clouds of gas. Can you imagine being able to know what a star is made of that you will never be able to touch, just by analyzing the light it emits or absorbs? Thus, light not only illuminates our path, but also tells us the deepest secrets of the universe, allowing us to read, like in an open book, the composition, temperature, and movements of objects that exist far beyond our physical reach. In summary, the interaction between light and matter is much more than a simple visual spectacle. It is a cosmic language that scientists have learned to decipher. Every absorption and every emission of light in the universe is a clue, a piece of a giant puzzle that helps us understand our place in the cosmos. Without these processes, the universe would be a much more difficult mystery to unravel and perhaps a little less fascinating. What are nebulas really? Many times we hear this term and think of colorful clouds floating in space. But why do they shine? And what is their function in the universe? Nebulas are enormous clouds of gas and interstellar dust, stretching across light years. If one could get closer, they would discover that, although they seem dense, they are actually extremely diffuse. A handful of Earth's air has more atoms than the same volume within a nebula. However, their colossal size makes them key elements of the cosmos. Why do some nebulas emit their own light, while others only reflect that of nearby stars? The answer lies in the physical processes occurring within them. There are emission nebulas, where the ultraviolet radiation from young, hot stars energizes the gas, making it glow in reddish or greenish tones. It's as if the stars are light bulbs that illuminate the clouds around them. In contrast, reflection nebulas are like cosmic mirrors. They do not generate light, but scatter the light from nearby stars, taking on a blue hue for the same reason that Earth's sky is blue, due to light scattering. But nebulas are not just beautiful landscapes, they are true stellar nurseries. How do new stars form within these cosmic clouds? When regions of gas and dust collapse under their own gravity, dense cores form that, upon heating, ignite the process of nuclear fusion. In other words, nebulas are the cradles where stars are born, and therefore planetary systems. Every star we see in the sky once emerged from a nebula, transforming dispersed material into bright and complex objects. Not all nebulas are the same. Some, like planetary nebulas, are the result of the death of stars similar to the Sun, which shed their outer layers and leave behind a glowing cloud. Others, like supernova remnants, are remnants of stellar explosions that scatter heavy elements throughout space. Each type of nebula tells a distinct story of the life cycle of stars and the chemistry of the universe. Ultimately, these clouds of light and dust not only beautify the sky, but also play a fundamental role in cosmic evolution, connecting the birth, life, and death of stars. What role does light play in the formation of planets? To understand this, we need to go back to the birth of solar systems. It all begins inside dense clouds of gas and dust called protoplanetary disks. These disks rotate around young stars and are true cosmic cradles, where light is much more than a mere spectator. It is an active force that shapes the destiny of future worlds. Ultraviolet light and stellar winds emitted by the young central star heat and disperse the material in the disk, causing dust grains to clump together into small aggregates. How do these tiny grains manage to become planets? The star's radiation plays a dual role here. On one hand, it helps to remove the lighter gas, allowing solid materials to concentrate, and on the other, it drives chemical reactions on the surface of the grains, creating complex molecules that will be essential for the future chemistry of the planets. A fascinating fact is that the position of a forming planet largely depends on how much light it receives from the central star. In the closer regions, intense light evaporates light compounds like water, favoring the formation of rocky planets like Earth. Further out, where the light is less intense, ices survive and accumulate, allowing for the creation of gas giants and icy worlds. It's as if light draws invisible boundaries that determine the type of planet that can be born in each region of the disk. Moreover, Light is the main tool that astronomers use to discover and study planets outside our solar system. When a planet passes in front of its star, it blocks a portion of its light. This faint flicker allows us to identify its presence and even analyze its atmosphere. Thanks to light, we have detected thousands of exoplanets and begun to decipher their composition and habitability. Thus, light not only gives rise to worlds but also allows us to find and understand them, illuminating the path to new frontiers in the exploration of the universe. What do the light of a distant star and the molecules floating in space have in common? The answer is fascinating. Light not only allows us to see the universe, but it is also the spark that triggers cosmic chemistry. In the vast clouds of gas and interstellar dust, where extreme temperatures reign and matter is dispersed, light acts as an invisible catalyst, capable of breaking atomic bonds, forming new molecules, and transforming matter in surprising ways. Without the presence of light, space would be a stagnant chemical laboratory, devoid of the molecular diversity we observe today. How can light change the chemistry of space? It all begins when a photon, that is, a particle of light, collides with a molecule. If that light is energetic enough, like ultraviolet light, it can strip electrons from atoms, breaking molecules and creating ions. This process, known as photoionization, is fundamental for the creation of complex molecules in space, and it is one of the reasons why areas near young stars are filled with chemical reactions. It's as if light functions as a key, capable of opening new pathways for compound formation. But light doesn't just destroy, it also builds. When a molecule absorbs the energy from a photon, it can reorganize its atoms and give rise to new structures. Thanks to this phenomenon, called photodissociation, molecules as simple as molecular hydrogen have formed in space, but also much more complex ones, including precursors to amino acids. In molecular clouds, these processes intertwine and generate a true chemical soup, where light is the head chef. Can life as we know it have its origins in this type of light-driven chemistry? Many scientists believe so. The interaction between light and matter in space is not only responsible for molecular diversity, but it also provides us with clues about the origins of life. Comets and asteroids, formed in the coldest and darkest regions of the solar system, have preserved molecules created by the action of light in remote space. When these bodies impact planets, they can sow essential ingredients for life, demonstrating that light is much more than mere cosmic illumination. It is a creative force that has shaped the chemistry of the universe and perhaps the emergence of life itself. What allows us to learn about the most spectacular events in the universe, even if they occurred billions of light years away? The answer is light. Light is, in essence, the cosmic messenger that carries stories from the farthest corners of the cosmos to us. Every photon that reaches Earth has traveled immense distances, overcoming obstacles and traversing space-time, to tell us a tale about the universe's past. When a gamma ray burst occurs, for example, we are witnessing one of the most energetic phenomena known. How do we know it happened? Because light, in the form of gamma rays, travels directly from that event to our telescopes. It's like receiving an urgent letter written in a language that scientists have learned to decipher. These bursts may last only seconds, but in that brief span, they release more energy than the sun will emit in its entire lifetime. The light we capture from these events allows us to analyze not only their origin, but also the extreme conditions that generated them. Galaxy collisions, on the other hand, may seem slow and silent, but they create an impressive luminous spectacle. What kind of signals does the universe send us in these cases? When two galaxies collide, their clouds of gas and dust interact, leading to the formation of new stars and emitting light across the entire electromagnetic spectrum. Astronomers can study these emissions to unravel how galaxies evolve and how stellar systems are born. Light, in this context, becomes a tool that reveals processes that would otherwise be invisible. Even the most exotic phenomena, such as the formation of black holes or the merging of neutron stars, leave their luminous mark. Why is light so valuable in these cases? Because it conveys information about chemical compositions, extreme temperatures, and astonishing speeds. Light can take many forms: X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. Each of these voices tells a different part of the universe's story. And like in a mystery novel, scientists must piece together all the luminous clues to reconstruct the grand cosmic events. In the end, light is much more than just something that allows us to see. It is the universal communication channel between the stars and our curiosity. Thanks to light, we can observe titanic explosions, births and deaths of stars, and signals that have traveled for billions of years to reach us. Thus, every time we look up at the sky, we are actually reading ancient messages written with light that narrate the living history of the universe. What makes the sun much more than just a bright sphere in the sky? The answer lies within. There, in its core, nuclear reactions occur so powerful that every second they transform millions of tons of hydrogen into helium. This process, known as nuclear fusion, releases an immense amount of energy in the form of light and heat. It is this light that travels for over 100,000 years from the center of the sun to its surface, and only after that long journey does it take just over 8 minutes to cover the vast distance that separates us. It is impressive to think that the light that warms us today began its journey before human civilization existed. But why is sunlight so crucial for life on Earth? Without it, our planet would be a cold, dark world, unable to sustain even the simplest forms of life. The light from the sun provides the energy necessary for plants to perform photosynthesis, the process that converts carbon dioxide and water into oxygen and food. Without this cycle, life as we know it would not exist. Furthermore, sunlight regulates the vital cycles of living beings, from the sleep of animals to the growth of crops that feed humanity. Did you know that sunlight is not white, even though we perceive it that way? In reality, it is composed of all the colors of the rainbow, a mixture of electromagnetic waves that range from red to violet. When sunlight passes through the atmosphere, air molecules primarily scatter the blue tones, which explains why the sky appears blue during the day. This phenomenon, known as Rayleigh scattering, is also responsible for the reddish and orange hues of sunsets. Thus, every sunrise and sunset serves as a daily reminder of the intrinsic complexity and beauty of sunlight. And what about the future of the sun? Although it may seem eternal, its life has a limit. In about 5 billion years, it will exhaust its fuel and transform into a red giant, leaving behind a white dwarf. However, for billions of years more, it will continue to be our source of light and energy. The sun is much more than just a star among many. It is the very reason for our existence, the clock that sets the rhythm of life, and the beacon that has guided humanity since its origins. Understanding its workings connects us to the cosmos and reminds us that, ultimately, we depend on the light of a single star. What natural phenomenon can paint the night sky with curtains of green, pink, or violet light, as if the Earth itself were celebrating a cosmic fireworks show? The auroras, known as the northern lights in the northern hemisphere and southern lights in the south, are one of the most astonishing encounters between the energy of the sun and the atmosphere of our planet. But what mysteries lie behind this display of lights? How does the interaction between space and Earth give rise to these hypnotic visions? It all begins more than 150 million kilometers away, at the sun. There, enormous amounts of energy are constantly released in the form of solar wind, a stream of charged particles, mainly electrons and protons, traveling at incredible speeds. When this solar wind reaches Earth, it does not do so without obstacles. Our planet is protected by an invisible shield, the magnetosphere, a bubble formed by the Earth's magnetic field. Why is this shield so important? Because without it, the Earth's atmosphere would be literally swept away by the solar wind, and life as we know it would be impossible. However, the magnetosphere is not impenetrable. Near the magnetic poles, the lines of the magnetic field open up and allow some of those solar particles to slip into the upper atmosphere. Upon coming into contact with the atoms and molecules of the air, mainly oxygen and nitrogen, these particles transfer their energy, causing the gases to emit light. It's as if each atom momentarily becomes a tiny colored light bulb. Oxygen typically emits green and red hues, while nitrogen produces blues and violets. Why are auroras more common near the poles? Because that is where the magnetic field directs most of the solar particles into the atmosphere. Auroras are not only a visual delight, but also a scientific window into the workings of the Earth and its relationship with the Sun. Studying auroras allows scientists to better understand solar storms, changes in the magnetic field, and the risks these phenomena pose to communications and technology on the surface. Did you know that during intense solar storms, auroras can be seen much farther from the poles, even reaching mid-latitudes? Furthermore, auroras show that our planet is not an isolated island in the cosmos, but is in constant interaction with the spatial environment. Beyond science, auroras have fascinated humanity since ancient times. Northern civilizations interpreted them as divine signs, omens, or dances of spirits. Today we understand that they are the result of physics in action, a visual reminder of the connection between the Earth and the Sun. Each aurora is a luminous message that speaks to us of the energy, magnetism, and beauty that exist in the universe, inviting us to look up and wonder in what other ways light can transform our planet. What is it about light that makes it the secret engine of life? At the heart of this mystery is photosynthesis, a process that, while seemingly simple, is one of the most extraordinary on the planet. Thanks to photosynthesis, plants, algae, and some bacteria can transform sunlight into food, converting solar energy into chemical energy. But how does this natural magic trick happen? It all begins when sunlight strikes chlorophyll, the green pigment found in leaves. That beam of light not only illuminates, but also knocks electrons loose and sets off a chain of chemical reactions that produces glucose and oxygen from carbon dioxide and water. Without photosynthesis, Earth would be a barren desert. This process not only nourishes plants, but also gives life to the entire food chain. Animals, including humans, indirectly depend on the solar energy converted by plants. It's as if plants are living solar panels, storing energy in their tissues that then travels through the ecosystem. This transformation is so fundamental that it has shaped the atmosphere and the evolution of life. Did you know that the oxygen we breathe is a byproduct of photosynthesis? Billions of years ago, the primitive atmosphere lacked free oxygen. It was cyanobacteria, through photosynthesis, that released oxygen and created the conditions necessary for complex life. Can light really change the fate of a planet? The answer lies in Earth's history. The emergence of oxygenic photosynthesis marked a turning point in evolution. The so-called Great Oxidation Event over 2 billion years ago radically transformed the atmosphere. This change allowed for the emergence of oxygen-breathing organisms and, over time, the explosion of biodiversity that characterizes our planet. Light, converted into chemical energy, became the foundation of the trophic pyramid, supporting everything from tiny bacteria to the largest predators. But photosynthesis is not only vital for life on Earth, it is also one of the keys to understanding the possibility of life on other planets. If we find signs of similar processes on exoplanets, we could have indications that light has also been the trigger for life in other corners of the cosmos. Thus, the story of photosynthesis is, in fact, the story of how a simple beam of light can give rise to the complexity, diversity, and wonder of life. How is it possible that the eyes of a fly, those of a fish, and those of a human, so different from each other, have the same purpose: to capture light? Vision, as we know it today, is the result of millions of years of evolution, a silent race in which life perfected its ability to read the messages that travel in the form of light waves. But when and why did vision arise on Earth? It all began in the primitive oceans over 500 million years ago. There, the first living beings could barely distinguish between light and darkness. However, that simple difference was vital. Light indicated the surface, a source of energy and food, while darkness could hide predators. Gradually, certain light-sensitive cells, the precursors of what we now call photoreceptors, began to cluster and specialize. Those rudimentary groupings evolved into simple eyes, capable of detecting the direction of light, and, over time, allowed for the distinction of shapes and movements. But how did we transition from a simple light-sensitive spot to organs as complex as the eyes of vertebrates? The key lay in the competition for survival. In a world where being seen could mean death and seeing before the other could be the difference between hunting or being hunted, evolutionary pressure favored the enhancement of vision. Thus, compound eyes emerged in insects, perfect for capturing rapid movements, and camera eyes in cephalopods and vertebrates, capable of focusing and distinguishing details. It is curious to think that the eyes of an octopus and those of a human, although very similar in appearance and function, evolved independently, a phenomenon known as convergent evolution. Vision not only allowed living beings to navigate and survive, but also opened doors to new forms of life and behavior. Colors, for example, became vital signals for communication, mate selection, or camouflage. Did you know that many animals see colors invisible to us, such as ultraviolet? This diversity of perceptions demonstrates that each species has adapted its vision to its own needs and environments. There are even creatures from the deep sea whose eyes are so sensitive that they can perceive tiny flashes in the abyssal darkness, where sunlight never reaches. In summary, the evolution of vision on Earth is a story of biological innovation and constant adaptation. From cells that could only distinguish day from night to eyes capable of capturing the beauty and complexity of the world, light has always been the great messenger, and vision, the language that life learned to decipher it. What other visual wonders await us to discover in the still unexplored corners of our planet? Have you ever wondered how our brain converts simple photons into the rich visual experience we live every day? The human eye is an evolutionary marvel, a sophisticated biological sensor that allows us to decipher the language of light. It all begins when light enters through the cornea and passes through the lens, a flexible lens that focuses the rays onto the retina, located at the back of the eye. The retina, far from being a simple screen, is lined with millions of light-sensitive cells, the cones and the rods. The cones allow us to distinguish colors and are mainly grouped in the center of the retina, while the rods, much more numerous, capture dim light and help us see in the dark. But how do we transform that information into images? In the retina, photons activate chemical reactions in the cones and rods, generating electrical impulses. These impulses travel through the optic nerve to the brain, where the real magic happens. Visual interpretation. The brain not only receives a signal, but integrates millions of them, reconstructing the environment with astonishing precision and speed. In fact, what we see is a processed and edited version by our brain, which fills in gaps, corrects errors, and provides us with a coherent and continuous perception of the world. Why do we see colors and how do we distinguish them? The cones are specialized in capturing different wavelengths. Some detect red, others green, and others blue. It's as if we have 3 types of antennas for light, and the combination of their activation allows us to perceive a wide range of colors. When we look at, for example, a red apple, the cones sensitive to red are activated more than the others, and the brain interprets that signal as red. However, this system is so complex that it can sometimes deceive us. The famous optical illusions are the result of how our brain interprets, or sometimes misinterprets, visual information. And what about the perception of depth or movement? Our eyes function like a pair of cameras, separated by a few centimeters. Thanks to the slight difference in the images that each eye captures, the brain calculates distances and creates the sensation of three-dimensionality. Additionally, specialized cells detect minimal movements, allowing us to react quickly to any changes in our environment. Despite all this precision, our visual field has blind spots, areas where we do not perceive an image. However, the brain automatically compensates for these gaps, providing us with uninterrupted vision. The human eye is much more than a simple light receptor. It is the result of millions of years of evolution, adapted to make the most of the luminous information in the environment. Our ability to perceive colors, shapes, and movements has been key to survival and the development of civilization. By understanding how this biological marvel works, we appreciate even more the importance of light, not only in life but in the way we experience and understand the universe. Have you ever stopped to think about why you feel more awake during the day and sleepy when it gets dark? The answer lies in the deep relationship between light and the biological rhythms that control our lives. These rhythms, known as circadian rhythms, are internal clocks that regulate fundamental processes such as sleep, wakefulness, body temperature, and even appetite. But how does our body know what time it is? The key is light, that silent signal that acts as the conductor of an orchestra, synchronizing every instrument in our organism. In humans, the light we perceive through our eyes not only allows us to see, but also sends direct signals to a small region of the brain called the suprachiasmatic nucleus. This tiny group of neurons is the true master clock. When the light of dawn reaches our eyes, this central clock adjusts the entire system, indicating that it's time to be alert and active. As night falls and light decreases, the body begins to produce melatonin, the hormone that induces sleep. Thus, light becomes the switch that turns on and off the different states of the body, ensuring everything functions precisely. But the influence of light goes far beyond humans. In nature, countless species depend on the cycles of light and darkness to survive. Birds migrate following the length of the days, plants open and close their flowers based on sunlight, and even some insects synchronize their reproduction with the phases of the moon. It's as if the entire planet is connected by an invisible melody in which light sets the tempo. This synchronization ensures that living beings are in the right place at the right time to feed, reproduce, and protect themselves. So what happens when we disrupt these cycles with artificial light? Nowadays, exposure to screens and electric lights can confuse our internal clocks, leading to insomnia, fatigue, or even more serious health issues. Scientists are studying how light of different colors and at different times affects our physical and mental well-being. For example, the blue light emitted by electronic devices is especially effective at suppressing melatonin, delaying sleep. Thus, understanding how light regulates our biological rhythms is not only fascinating, but essential for taking care of our health in the modern world. What would humanity be without light? Since ancient times, light has fascinated all cultures. Why does the sun shine? What mysteries lie behind the rainbow? In antiquity, civilizations like the Egyptians and Greeks regarded light as a symbol of life, divine power, and knowledge. Fire, the first artificial source of light, not only allowed our ancestors to drive away darkness, but also to expand their activities and transform their daily lives. Light became a metaphor for wisdom and revelation, inspiring myths, religions, and even immortal works of art. But how has light transformed the course of human science? The study of light was one of the great engines of the scientific revolution. How do we know that light can behave as both a particle and a wave? Throughout history, brilliant minds like Isaac Newton and Christian Huygens debated its true nature. Later, Albert Einstein demonstrated that light is the key to understanding the very structure of space and time. Thanks to light, humanity has been able to measure astronomical distances, discover the chemical elements of stars, and unravel the composition of distant atmospheres using the spectrum of colors. Light has also marked milestones in technology and communication. What would the world be like without photography, cinema, fiber optics, or lasers? From the first daguerreotype to the screens of our devices, the manipulation of light has changed the way we see and share the world. The invention of the electric bulb transformed cities and lifestyles, allowing for the expansion of industry and nightlife. Beyond that, laser light has revolutionized medicine, telecommunications, and space exploration, opening pathways that we could only imagine before. Despite its omnipresence, light remains a bridge between mystery and knowledge. Why do colors affect our emotions? How does light influence artistic creation and the perception of reality? From the stained glass of medieval cathedrals to contemporary art installations, light has been the raw material for expressing ideas, provoking sensations, and connecting cultures. In science, it remains the primary tool for observing the invisible, challenging the limits of our understanding, and opening new questions about the universe and our place in it. What would modern astronomy be without light? For centuries, light has been the main messenger between the universe and humanity. But how have technological advancements transformed our ability to read these cosmic messages? Today, modern astronomy relies on light to decipher the deepest secrets of the cosmos. Astronomers are no longer limited to observing the sky with the naked eye. They now use instruments capable of capturing the entire electromagnetic spectrum, from the longest radio waves to the most energetic gamma rays. Each type of light reveals a different face of the universe, as if each color and frequency were a distinct page of a cosmic book. Did you know that, thanks to light, we can know what stars are made of, how they are born and die, or even how distant galaxies move? Light, when interacting with matter, carries encoded information imprinted in its spectrum. Modern telescopes function like gigantic electronic eyes, capable of collecting and analyzing that light with astonishing precision. For example, by analyzing small shifts in the frequency of light emitted by a galaxy, astronomers can calculate how fast it is moving away from us, thus confirming that the universe is expanding. It's as if light were a conveyor belt bringing us fresh news from the farthest reaches of space and time. Is it possible to see the invisible universe? Although the answer may seem contradictory, modern astronomy has managed to observe phenomena that our eyes could never detect. Radio telescopes capture signals from clouds of cold gas. Infrared telescopes reveal baby stars hidden behind interstellar dust, and X-ray and gamma-ray detectors allow us to study the most violent events, such as supernova explosions or black hole activity. Each of these lights shows us a different perspective, as if there were multiple overlapping universes waiting to be explored with the right tool. But how can we ensure that the information we receive is accurate? Modern astronomy relies on sophisticated techniques to filter and correct the distortions that the Earth's atmosphere introduces into the light coming from space. That's why observatories are built on mountaintops or even in space, where the atmosphere is no longer an obstacle. Thus, light travels for billions of years only to be captured by a human detector, allowing us to reconstruct the history and structure of the universe. Without light and the ability to interpret it, modern astronomy would be like trying to read a book in complete darkness. What do a curious scientist and a child gazing at the stars have in common? Both dream of discovering what lies beyond what their eyes can see. But how do we manage to observe the deepest secrets of the universe when our views are limited by the Earth's atmosphere? The answer lies in space telescopes, true explorers of light that have revolutionized our understanding of the cosmos. Why do we send these instruments into space and not settle for powerful ground-based telescopes? The atmosphere is not transparent to all light. It absorbs, distorts, and blocks many wavelengths. It's like trying to see a landscape through a foggy glass. Space telescopes eliminate that obstacle and show us the universe in all its splendor. One of the most iconic names in light exploration is the Hubble telescope. Launched in 1990, Hubble has allowed us to observe galaxies billions of light years away and capture details that were unimaginable. Thanks to it, we have witnessed the birth and death of stars, the collision of galaxies, and have calculated the age of the universe with greater precision. But what makes Hubble so special? Its ability to capture visible, ultraviolet, and infrared light without atmospheric distortions makes it a kind of optical time machine, allowing us to see what the universe was like in its early stages. What if we want to look even further or capture forms of light that Hubble cannot see? This is where the James Webb Space Telescope comes into play, launched in 2021. This gigantic observatory, with a golden mirror over 6 meters in diameter, is specially designed to observe in the infrared. Why is infrared so important? The light from the most distant objects in the universe, due to cosmic expansion, is stretched and shifted toward the infrared. The James Webb can detect that ancient light, allowing us to observe the first galaxies that formed after the Big Bang and study the atmospheres of exoplanets in search of chemical signatures of life. But space telescopes are not limited to Hubble and James Webb. There are others like Chandra, specialized in X-rays, and Spitzer, focused on infrared, each opening unique windows to the universe. Thus, light in all its forms becomes a tireless messenger that travels for billions of years until captured by these artificial eyes. Can you imagine all that these instruments will continue to reveal in the coming years? Thanks to space telescopes, humanity has learned to read light like an open book, deciphering the mysteries that lie beyond the borders of our planet. Ultimately, space telescopes are a testament to our insatiable curiosity and our creativity to overcome limits. Each new image, each piece of data collected, not only teaches us about distant stars and galaxies, but also reminds us how small our place is in the universe and how great our capacity to explore is. The exploration of light from space has been, and will continue to be, one of humanity's most exciting scientific adventures. Have you ever wondered how astronomers know the composition of stars located millions of light years away? The answer lies in a revolutionary tool: spectroscopy. Far from being a complicated name, spectroscopy is essentially the science of breaking down light into its colors, as if we had a giant prism capable of revealing the hidden secrets in every ray of light traveling through the universe. Just as a detective analyzes clues at a crime scene, scientists examine the traces left by light as it passes through different materials to decipher the history and nature of cosmic objects. But why are colors so important? Each chemical element in the universe leaves a unique signature, a kind of barcode that appears as bright or dark lines in the light spectrum. When the light from a star passes through a prism or a grating, it disperses into a range of colors, and in that display, specific lines appear that correspond to the presence of hydrogen, helium, oxygen, or even heavier elements like iron and calcium. This way, astronomers can know not only what is in a star, but also at what temperature it burns, how fast it moves, and even if there are planets around it. Did you know that thanks to spectroscopy, we discovered that the universe is expanding? When we analyze the light from distant galaxies, we observe that the lines in their spectrum shift towards the red, indicating that they are moving away from us. This phenomenon, known as redshift, was one of the keys to understanding the evolution of the cosmos. Furthermore, spectroscopy allows us to detect atmospheres of exoplanets, search for organic molecules in nebulae, and even capture the imprint of stellar explosions that occurred billions of years ago. Spectroscopy is not just a tool for looking far, it also helps us look deep. It allows us to identify the presence of water in a comet's tail, distinguish between a young star and an old one, or discover the composition of Saturn's rings without needing to travel there. It's like having a secret language that can only be read through light, and that speaks to us about the history, evolution, and mysteries of the universe. Without spectroscopy, the cosmos would be a silent and detailless stage. Thanks to it, the universe tells us its story in full color. What does light have to do with gravitational waves? At first glance, they seem like completely different phenomena. One is the vibration of space-time itself, the other an electromagnetic oscillation. However, when a truly extreme cosmic event occurs, such as the merger of two neutron stars, both types of signals are generated almost simultaneously and travel through the universe like two messengers, bringing us stories about what just happened. But why is this so revolutionary for astronomy? Until very recently, everything we knew about the cosmos came from light in its various forms: visible, infrared, X-rays, or gamma rays. It was like trying to understand a movie using only the sound. But in 2015, the LIGO detectors captured gravitational waves for the first time, created by the collision of two black holes. What does this mean? That for the first time we could hear the universe, not just see it. A couple of years later, in 2017, an even greater milestone occurred. The collision of two neutron stars was detected almost simultaneously by both gravitational waves and light, opening the era of multi-messenger astronomy. Why is it so important to capture both types of signals? Imagine witnessing an accident in the distance. If you can only see it, you will know what happened. But if you can also hear it, you will have much more information about the causes and consequences. In the case of neutron star mergers, gravitational waves reveal details about the masses and orbits of the objects before the collision, while light, especially gamma-ray bursts, and the subsequent glow, tells us about the formation of heavy elements like gold and platinum, and how matter is dispersed in space. This combination of messages has allowed us to confirm fundamental theories, such as that certain short gamma-ray bursts come from the merger of neutron stars. Additionally, it has provided a new way to measure cosmic distances and even calculate the expansion of the universe. Light and gravitational waves together offer us a much more complete and detailed view of the most violent and energetic events in the cosmos, allowing us to answer questions that for centuries seemed impossible. How do the heaviest elements form? How does matter behave under extreme conditions? And what is the true nature of gravity? Thus, the arrival of gravitational waves has not replaced light as our window to the universe, but has complemented it in an unexpected way. Now, every time the universe vibrates and shines at the same time, we have the opportunity to decipher its secrets with unprecedented clarity, as if we could finally see and hear the cosmic symphony in all its magnitude. Are we alone in the universe, or are there other civilizations looking up at the sky, wondering the same? Light, that universal messenger, plays a key role in the search for life beyond our planet. Why light? Because it travels through space at incredible speeds and can carry encoded information, artificial signals, or simple traces of technological activity. If an advanced civilization wanted to make itself known, light would be its most effective tool, as if they were lighting a cosmic beacon in the midst of vastness. Scientists have developed fascinating strategies to search for signs of other intelligences using light. One of the most well-known is the search for optical signals, extremely brief and powerful laser light pulses sent deliberately. Why use lasers? Because they are much easier to distinguish from the natural noise of the universe. If a civilization wanted to send an interstellar greeting, a laser pulse would be like a bright wink, impossible to ignore among the stars. This idea has driven projects like optical SETI, which scan the sky for light patterns that cannot be explained by natural processes. But light can also reveal the presence of civilizations indirectly. How? By observing the atmosphere of exoplanets for unusual chemical compounds, such as industrial pollution. If we detected gases like chlorofluorocarbons, which are only produced artificially on Earth, it would be a tantalizing clue. Moreover, light coming from large artificial structures, like hypothetical Dyson spheres, gigantic constructions that would envelop a star to capture its energy, could alter the brightness and spectrum of the star, betraying the existence of advanced technology. The question is, how likely are we to see these signs, or are we searching for a needle in a cosmic haystack? Even the absence of light can be revealing. Imagine detecting a planet passing in front of its star, and suddenly its brightness decreases strangely or regularly, as if something artificial were blocking it. Could these be structures of technological origin? This type of unusual pattern has sparked passionate debates among astronomers, always eager to rule out natural explanations before dreaming of extraterrestrial civilizations. In the end, light is our bridge to the unknown. Every photon we capture could carry unimaginable secrets. Is it possible that, in some corner of the cosmos, there is someone sending signals waiting to be discovered? Or perhaps we simply have not yet learned to listen to the messages that light whispers to us from distant minds. The search continues, and light remains our best ally in finding answers in the vast darkness of the universe. Have you ever stopped to think about how humanity has gone from relying solely on the light of the stars and fire to creating its own sources of illumination? The invention of artificial light radically transformed everyday life. From the first torches and oil lamps to the electric bulb, mastering light became one of the most significant technological advancements in our history. But why was it so revolutionary to be able to generate light at will? The answer is simple. It allowed human activity to extend beyond the natural cycle of day and night, driving the development of cities, industries, and entirely new ways of life. The technology of light did not stop with the invention of the bulb. Did you know that today we use lasers in applications that go far beyond office pointers? Lasers enable high-precision eye surgeries, reading barcodes in supermarkets, and transmitting information at incredible speeds through optical fibers. These fibers, thin strands of glass, carry pulses of light that contain data, phone conversations, videos, even this script. Thus, information literally travels at the speed of light, interconnecting continents and enabling the digital age we live in. Artificial light has also opened the doors to amazing fields like photonics, where traditional electrons in electronics are replaced by photons. What advantages does this have? Photonic devices promise to be much faster, more efficient, and compact, which could revolutionize computing and communications. Imagine computers capable of processing information thousands of times faster than current ones, or data networks that are practically instantaneous. Moreover, light is used to create smart environments, adjustable intensity lamps, efficient LED lighting, and systems that regulate light according to people's biological rhythms, enhancing well-being and performance. But where will artificial light take us in the future? Scientists are exploring new sources of illumination, such as organic light-emitting diodes, which could lead to ultra-thin and flexible screens, or even luminous paper. Quantum manipulation of light opens the possibility of absolutely secure communications thanks to quantum entanglement. And in space exploration, artificial light is key. Lasers are used to transmit data from interplanetary probes, and solar sail propulsion is being researched, which harnesses light pressure to propel spacecraft through the vacuum. Thus, artificial light, far from being just an everyday tool, has become one of the main engines of human innovation, illuminating not only our environment, but also the path to the future. Is there a limit to how far we can see in the universe? Although light is our main cosmic messenger, we cannot observe everything we would like. The first major obstacle is the age of the universe itself. Light takes time to travel, so we can only see objects whose light has had enough time to reach us since the Big Bang. That's why looking into deep space is like looking into the past, but we can never see beyond a certain cosmic horizon. It's like trying to read a book from the last page. You can only know what has been written up to that point. The rest is still blank for us. But even within that theoretical limit, there are barriers that complicate our vision. For example, there is a time known as the surface of last scattering, which marks the farthest boundary we can observe with light. Before that moment, the universe was so dense and hot that light could not travel freely. It constantly collided with charged particles, as if we were trying to see through thick fog. That's why the cosmic microwave background is the oldest thing our instruments can detect with conventional light. Beyond that wall, information becomes unreachable for optical and microwave telescopes. And what about the light that should reach us, but we never see? Here another factor comes into play: the absorption and scattering of light by interstellar dust and gas. Large clouds of material can block or obscure the light from distant objects, especially at certain wavelengths. It's like trying to see a lighthouse from a port through a sandstorm. The signal weakens, distorts, or even disappears completely. That's why astronomers use different types of telescopes, X-ray, infrared, ultraviolet, to try to see through these obstacles, although each has its own limits. Finally, the very nature of light imposes fundamental restrictions. As the universe expands, the light from extremely distant objects stretches, shifting to longer wavelengths until it becomes invisible to our current instruments. This phenomenon, known as redshift, means that there are events and structures so distant that their light, no matter how long it has traveled for billions of years, can no longer be captured. Thus, while light reveals the secrets of the cosmos to us, it also confronts us with a wall of mystery, reminding us that, for now, there are regions of the universe that will forever remain beyond our visual reach. What are the brightest and most extreme objects in the universe? To answer this question, we must delve into the fascinating world of pulsars and quasars, two types of cosmic beacons that challenge our understanding of light and energy. Both are testaments to the most violent and energetic processes occurring in the cosmos, but their origins and functions are radically different. Let's start with pulsars. Is it possible for a star, upon dying, to become a cosmic metronome? Pulsars are precisely that, remnants of massive stars that exploded as supernovae, leaving behind an ultra-compact core known as a neutron star. These objects, with a mass greater than that of the Sun, compressed into a sphere of just about 20 kilometers in diameter, rotate at dizzying speeds and possess enormous magnetic fields. As they spin, they emit beams of electromagnetic radiation from their magnetic poles. If Earth is in the path of that beam, we observe regular pulses of light, as if it were an intergalactic lighthouse. Some pulsars rotate hundreds of times per second, making them cosmic clocks of astonishing precision. But if you thought pulsars were amazing, quasars take spectacularness to another level. How can an object at the center of a galaxy outshine the combined light of hundreds of billions of stars? Quasars are active galactic nuclei powered by supermassive black holes. The gas and dust falling into these black holes release a colossal amount of energy, heating up to millions of degrees and emitting light so intense that it can travel billions of light years across the universe. In their most active periods, quasars shine with a brilliance that defies imagination. For a cosmic instant, a single region the size of the solar system can outshine its entire host galaxy. What use do we have in detecting these extreme phenomena? Pulsars have allowed astronomers to confirm the existence of gravitational waves and study the limits of physics under conditions impossible to recreate on Earth. On the other hand, quasars function as beacons in the darkness of the early cosmos. By analyzing their light, it is possible to study the composition and evolution of intergalactic gas throughout the history of the universe. Additionally, the regularity of pulsars has made them potential tools for interstellar navigation, as if they were buoys in a cosmic ocean. Ultimately, pulsars and quasars remind us that light is not only a messenger of everyday life, but also the trace of the most extreme and exotic processes in nature. These cosmic beacons, so distant and mysterious, help us decipher the secrets of the universe and understand how far the creativity of physics can go when matter and energy are pushed to the limit. What happens when matter comes face to face with its perfect opposite, antimatter? This question has fascinated scientists for decades, and its answer reveals one of the most impressive phenomena in the universe: annihilation. When a matter particle, such as an electron, encounters its antiparticle, the positron, both disappear in an instant, releasing their energy in the form of light, usually as gamma photons. It's such an efficient process that all the mass is transformed into pure energy, according to Einstein's famous equation, E=mc². Can you imagine if we could harness all the energy contained in matter this way? But how do we know that antimatter exists, and that it can actually produce light when it combines with matter? Physicists have created and observed antimatter in laboratories such as CERN, where antiparticles are generated in colliders and their interactions are studied. Moreover, in the universe, annihilation occurs naturally. For example, when cosmic rays collide with the Earth's atmosphere, pairs of electrons and positrons can be created that, upon meeting, annihilate and emit gamma rays detectable from space. Even in some hospitals, PET, positron emission tomography, technology uses this principle to obtain images of the inside of the human body, thanks to the light generated in these reactions. And why isn't the entire universe filled with light created by annihilations? Here arises one of the great mysteries of cosmology. Apparently, at the origin of the universe, there was almost the same amount of matter as antimatter, but for some unknown reason, matter won the battle. Today, antimatter is extremely rare, and when it appears, as in some processes in the centers of galaxies, it quickly encounters matter and both disappear in bursts of energy. If the amount of antimatter were greater, the universe would be radically different, perhaps even inhospitable to life as we know it. Matter-antimatter annihilation is much more than a mere curiosity. It is a direct window into the conversion of mass into energy, and a reminder of the deep symmetry, and also the asymmetry, that governs the cosmos. Furthermore, studying these processes helps us understand everything from the gamma rays that reach us from space to the most extreme and energetic events, such as gamma ray bursts, and the mysterious sources of light at the center of the Milky Way. The light born from annihilation not only illuminates space, but also sheds light on the fundamental enigmas of existence itself. What does the future hold for the study of light? Have we already reached the limit of what we can discover, or are we just scratching the surface of its secrets? Light, that tireless messenger of the universe, continues to present us with new challenges and mysteries to solve. One of the great dreams of science is to capture the oldest and most distant light, the kind that would allow us to peek into the very first moments of the cosmos, even before the formation of the first stars. But how could we achieve this if even our most advanced telescopes encounter barriers in cosmic dust and the expansion of the universe? The answer may lie in the development of even more sensitive detectors and the use of new technologies based on quantum physics, capable of distinguishing extremely faint signals from the cosmic background noise. On the other hand, light is not only a tool for observation, but also a key to manipulating matter and information. What if we could create telescopes that used quantum interferometry to obtain much more detailed images than the current ones? This technique, which takes advantage of the wave-like and quantum nature of light, would allow us to observe details that today seem unattainable, such as the atmosphere of distant exoplanets or signs of life around other stars. Furthermore, the use of increasingly precise and powerful lasers could open the door to unprecedented experiments, from the creation of exotic matter to simulating extreme conditions of the early universe in terrestrial laboratories. The search for life beyond Earth will also be revolutionized by the advanced study of light. Soon, next-generation spectroscopes will be able to analyze the composition of planetary atmospheres with such precision that it will be possible to detect the chemical fingerprints of biological processes. Will we be able to identify the presence of oxygen, methane, or water hundreds of light years away? Each advance in the sensitivity and resolution of our instruments brings us one step closer to answering the big question: are we alone in the universe? And if we ever detect an artificial light signal coming from another corner of the cosmos, we could be facing the most transformative discovery in human history. The future of light study also involves discovering new forms of energy and communication. Photon-based technologies could revolutionize telecommunications, allowing information to be transmitted at speeds close to the universal limit. Additionally, light could be the key to deciphering the nature of dark matter and dark energy, those invisible components that dominate the universe, and that, until now, we can only infer by their effects on the light that reaches us from distant galaxies. In summary, light not only illuminates our path to the cosmic past, but also points to the roots of knowledge and innovation that will transform our future. How far will our ability to unravel its secrets go? Only time and light itself will have the final word. What would the universe be like if light did not exist? Without it, the cosmos would be an unfathomable enigma, a silent orchestra of matter and energy without a visible score. Light, in all its forms, has been the tireless messenger connecting the most distant events of space-time with our human curiosity. From the primordial explosion that gave rise to everything to the flashes of distant galaxies, light has been the thread that weaves the cosmic history, revealing the secrets hidden in the vastness of the universe. Did you know that every beam of light we perceive carries invaluable information from the past? Observing the sky is, in fact, traveling through time. When we look at a star, we are seeing how it was thousands, millions, or even billions of years ago. Light is like a letter sent from the distant past, traversing abysses of darkness to reach us and tell us the story of its origin. Thus, we have learned about the birth of stars, the formation of planets, the life cycle of elements, and the existence of phenomena as strange as black holes and supernova explosions. Can light explain everything about the universe? While it is our best guide, it also reminds us of how much we have yet to discover. Sometimes, light disappears, bends, or transforms, revealing the presence of mysteries like dark matter and dark energy, invisible yet fundamental components of the cosmos. Light then becomes an unrelenting detective, leaving subtle clues along its path, such as redshift, traces in the cosmic microwave background radiation, or the absorption and emission patterns of distant nebulae. Each of these hints pushes us to rethink our theories and seek deeper answers. Throughout history, light has been a source of wonder, inspiration, and knowledge. It has allowed life to flourish on Earth, guided the evolution of the senses, and driven the development of human civilization. Without light, science as we know it would not exist, nor would our ability to explore beyond our own planet. And although the current limits of observation prevent us from seeing everything we would like, the search continues. What secrets still await us at the edges of the universe? Light, always a tireless traveler, remains our compass to navigate the cosmic ocean, inspiring us to look up and ask, what else can we discover?